She's an assistant professor in the Institute of Automation and Infocommunication at the University of Miskolc, Hungary. Her field is modeling and control and trajectory optimization of dynamic systems in autonomous vehicles and serial robots. She earned a PhD in robotics in 2021, where the research focused on collaborating robot arm using AI techniques. Since 2021, she has been actively engaged in teaching and research at the Institute of Automation and Infocommunication, where she led courses on automation, robotics, and embedded systems. Furthermore, she actively participates in diverse projects related to the gas and oil industry, drone navigation, and AI and ML related to healthcare. She served as a sessions chair, organization committee member, and editor in ICCC 2023. She has published more than 20 peer-reviewed journal articles and conference papers in these domains. Today, she's going to talk a bit about optimal control and learning for Lego locomotion. So, put your hands together for Professor Rabab.
Good evening, dear audience. So today, I would like to explore with you the potential of collaborative robots. The content of my presentation will include several points. Okay, I will not go so deeply in it. I will just highlight the concepts. First of all, I would like to give a brief summary about a robotic arm, then identify together what is a cobot system, compare the cobot with the traditional industrial robot from the old fashion, and then we see the safety features of cobot system, the advanced sensor behind the successful of safety features, and the control strategies that should be taken into consideration with these kind of systems. After that, I would like to conclude my presentation with my actual research, where I would like to raise a question that if already the industrial market, the robotic industrial market, has developed and designed millions of industrial robotic arms, is it possible to upgrade these robots to be cooperative and smarter than building new ones from scratch? So we will answer on this question from this presentation. So if we see in the through the historical line of the industry, as you know, we are in the age of 4.0. A lot of concepts are highlighted here: digital twin, cybersecurity, Internet of Things, and cobot systems, where the cobot systems, it seems, they are everywhere in different industry sectors like healthcare sector, automotive sector, and even in space industry. Let me identify that regarding industrial robots, we have three categories. We find mainly serial robots, parallel robots, hybrid robots. This kind of categorization is related to the structure, the mechanical structure of the robot itself. In this presentation, I am dealing with robotic arm and collaborative robot arm. So, two concepts should be highlighted, and we should be familiar with it. The first concept is serial open chain structure. As you can see, the robotic arm is taken its name from the human arm. Even the name sets are the same. We have shoulder joint, we can find elbow, wristy, and as well. The structure here is serial open chain. It means that we have a base, a fixed base, and that base is connecting with different joints and links in serial way. Why is important to know that? Because to know the structure of the robot, you can model your mathematical modeling. You can identify your dynamic model, which is important to identify your torque to move these joints and links. The second concept is degree of freedom, DOF. When we are meeting with a robot, we say in industry or in the lab that this robot arm is with 5 DOF, 6 DOF. The 5 DOF and 6 DOF related to the degree of freedom. The degree of freedom is related for the object. the object in the 3D space, it should have 6 degrees of freedom. 3 translations around x, y, and z, and 3 rotations around x, y, and z. For the robotic arm, every joint can receive 1 or more degree of freedom, just like a human arm. For example, if I take the shoulder of a human arm, how many degrees of freedom I have here in my shoulder?
3.
Yes, we have 3. Rotation around this axis, rotation around this axis, and rotation around this axis. So we have 3 degrees of freedom. The robotic arm also can receive, for every joint, can receive 1 or more degree of freedom. Mainly, what we meet is a robotic arm with 5 degrees of freedom, where every joint includes 1 degree of freedom. These joints are moving with a motor, of course, and the motor compartment is including, as you can see, an encoder, which measure the position and the velocity, the angular position and velocity. We have the motor itself and the gear head to increase or decrease the ratio of the torque or the speed, and sometimes the drive here, driver of the motor. So, if we start to talk about Cobot, actually Cobot is a robotic arm, but with some advanced features to be friendly with the human worker. It's lightweight. If I can see from the first appearance, when I see a robot arm, I can identify if it's traditional one or Cobot. How I can recognize this? From the shape. Mainly they have a curvature shape, not sharp edges. They are with lightweight material, compact, with compact size. They don't need extensive space to be installed. And they provide very good safety feature. Like the safety is the most important feature in Cobot, where, for example, if I am close to the robot or nearly close, the robot should stop or decrease the speed. Okay, this is a video. It will not do it. Okay, and here also in this slide, I am showing the top leader in Cobot systems, which is Universal Robot. As you can see here, this is the newest one, UR20. If you see the characteristics, is heavy. It can handle heavier payloads and it can be faster. Let me now go more deep, where Cobot systems start to appear since 10 years, where traditional robotic arms are here since decades. So I think it's important to know what is the main differences between these two systems. The comparison will be regarding the hardware, the software, and the graphical user interface programming environment. So let's start with traditional robot. As you can see here, from the first appearance, the body is big. Usually it's more than 2 meters. And with the hard material, you can see it's a hollowic shape, which can harm easily the person. This is why we need fences. When we install a robotic arm in industry, you need fences, you need safety sensors, like laser scanner, like light curtains, just to avoid the risk for harming the worker. Okay. Also, here, mainly the motor are servo motors. Why servo motors? Because in industry, let's say in automotive industry, okay, I have many robotic arms. They are handling doors of car, they are welding. My important parameter is the precision. I would like to have precision regarding the position. So this is why I use servo motor. Servo motor is kind of motor which include a closed control loop for the position. So it can provide good precision, but they are heavier. But we don't care, because here we are using hard material, so the servo motor is okay. Also, these kind of robots require very good expertise to program. It's not easy to program. First of all, the programming is through the teach pendant we name it online programming. It can be also offline through the software, but 90% we program these kind of robots with the teach pendant, and the teach pendant is not so friendly. For example, here you can see that we have sometimes a lot of keys in the teaching pendant, and to create position, you have to take your teach pendant and you start to go to the P1, then P2, then P3, then make the trajectory, the circular or the linear according to your requirements. So it's not so friendly, and it needs time. Where for the cobot, we said that it's compact, it doesn't need a lot of space to install. Mostly we use brushless DC motors in the joints, mostly, not every time. Why? Because sometimes I would like to create compact size, so I don't need a big motor. This is related to the design, the body design. Also, a brushless DC motor can provide a good control speed. The motors here are not equipped only with encoders. There are more advanced sensors that we will see later on. And for the programming, it's very easy. It doesn't need good expertise, where here the teach pendant, as you can see, it's very intuitive and doesn't really need good expertise. Okay, and another good feature that I really like in the cobot is to create your trajectory or to execute your trajectory from the cobot. There is a function, we name it hand guidance. This function is just by clicking on the head of your cobot and you start to guide according to the trajectory. And somehow I am teaching my cobot how it takes the trajectory and it can execute it. This is because it has a free motion mode and it can help. So to say that I have a cobot and I could build a cobot, of course there is ISO. According to ISO standards, certified cobot must provide at least one of 4 safe collaborative applications. The first function is safe stop. Okay, everything can be stopped with emergency stop button, but in cobot, the cobot itself can provide this stop function. If I am getting very close to the cobot will stop by itself, or I can with emergency stop button, of course. The second feature is the hand guidance. This video shows you how the worker teaching the robot the trajectory. We have also speed and separation tracking. For example, this is my cobot and this is my workspace. This feature can allow the cobot to divide the workspace to zones. We have zone 1, zone 2. So the robot in zone 1 maybe will execute trajectory in some velocity, and in zone 2, it changed the velocity. So this is speed and separation tracking. And we have power and force limitations. This is when I go close enough to the cobot, it will not stop directly. There is here limitations in the joints. And these features are realized by the advanced sensors included in the cobot. The most important sensor that should be included in the cobot is force or torque sensors. Torque sensors are used to detect conditions where the torque level is high enough. So if the torque is high enough, the robot will stop or will decrease the velocity. We have also vision systems, of course. Vision systems can allow us to create computer vision algorithms. Why? To avoid collision or to see, like to detect an object, a worker, and it can stop. We have as well proximity sensors or lidars. Lidars are kind of sensor that measure the distance using laser. Beside the hardware, of course, we should implement some software, some techniques. Here I would like to highlight about collision avoidance, which is also very important in cobots. collision avoidance, and trajectory planification. Last year, I met with this software, which was launched by Real-Time Robotics in 2021, and it's just amazing solution for robotic arm and for industrial robotic arm and for cobot, because Real-Time Robotics, they launched two solutions, Rapid Plan and Rapid Sense. They are working together. Rapid Plan is a kind of software which can calculate in real time the optimal trajectory for the robot. And Rapid Sense, by cooperating with the 3D cameras, they can identify the objects, like the worker, anything in the working space, and they can send the data to the Rapid Plan, and the Rapid Plan can create, in the same time, the right algorithm to avoid that obstacle. So it's just amazing. Also, because we are in the world of DIY, do it by yourself, we can somehow create something like this. How? By using camera, and we can create using computer vision algorithm or genetic algorithm. We can also plan our trajectories. For control techniques, in cobot, actually we try to not use a simple PID controller. We go more deep, so we use advanced control techniques. Why? Because for cobot, I am focusing on the torque, how it is, the forces exerted by every joint. So in case of someone come or obstacle come, I would like to stop, I would like to decrease the motion. Therefore, I need to handle force control techniques. Some techniques like model predictive control, adaptive control, impedance, robust control are the best, or also reinforcement learning, which shows recently its potential in the field of controlling dynamic systems. So as you can see here, this is a loop. We have here a robot. This is the servo motors, for example, and here we have an MPC controller. And the MPC controller has a function to optimize. It can be anything, like you can set it. In this case, I am handling the function of torque to optimize the energy consumption. And now I come to this question. After checking the differences between traditional robotic arm and the cobot system, is it possible to upgrade a traditional robot to be smarter and cooperative? By my perspective, from my perspective, I think for a huge robotic arm, which can be found in automotive industry, for example, it's hard. It cannot be. Why? Because even if I will add the advanced sensors, the computer vision, I need also safety sensors, as you can see here. This is laser scanner. I will have the same body. I will have the same hollowick and sharp edges. So the risk will be there always for the human operator. But for small bodies, like this is also traditional robotic arm, by the way, but with smaller version. We have here KUKA, ABB, Fanuc, and Mitsubishi. I think it can be. And this is my actual research, by the way. In our lab, we have a very old robotic arm, which is from Mitsubishi, RV2AG 5 DOF. It has 5 degrees of freedom, of course, 5 rotational joints, very old controller, and very old teach pendant. And I said, why not? Why not make this robot more cooperative? So I started to order these kind of devices. First of all, I would like to deal with the torque sensor, because I would like to measure the torque in every joint. Here there are two solutions. There are this solution, torque sensor. If you go with this solution, you have to integrate this sensor in every joint. The second solution is provided by Universal Robot. This sensor is force torque sensor. it can measure in 6 axes, as you can see. And if you use this sensor, it should be integrated in the end effector, as you can see. As well as, I wanted to change that controller. That old controller it doesn't work. It doesn't give me what I want. So I am planning to use PLC from Phoenix Contact. Why this controller? Because there are 2 points. The first point, this PLC has a software, which is PLC Next Engineer. And Phoenix Contact created a very nice solution that PLC Next Engineer can be synchronized with MATLAB Simulink. If there is such a synchronization, it's great for me because I am a MATLAB lover. Usually I build my models there, I simulate them. So if I can import the Simulink model to PLC Next Engineer and then download it in this PLC, it's just the best. Also, this PLC, it provides the safety features. You can add a module for safety PLC relay, so it can be certified as a safety system. As well as, I would like to use Microsoft Kinect sensor. Microsoft Kinect sensor here for vision and for measuring the distance. Here there are 2 hypotheses in research. There are some who said that it's better to put the camera in the head of the robotic arm. Others, they said it's better to make it in a fixed position. I will go with this direction because I don't want to make it more complicated. I will focus just on a small area and try to control and to make the tests in a very fixed area. Mainly, this is the plan. As you can see here, this is the PLC, okay? And by the way, this PLC Next, this controller, it can be also synchronized with ROS. So here you can see that I can put my safe IOs, emergency stop buttons and stuff. I can also put the IOs of the robotic arm. I can add the sensors like encoders, laser scanner. And this is the plan. The plan is having the dynamic model of RV2AG. It's done. It's in my packet. I created the model predictive control. I started to use model predictive control because I wanted to make some tests. And I am in this phase importing the Simulink model in PLC Next Engineer to download it in the PLC. This results was published this year. It's a comparison between PID and model predictive control. As you can see, this is the loop was created in MATLAB Simulink. Actually, I wanted to test. I gave 3 trajectories: curvature trajectory, N-shaped trajectory, and the circle trajectory. And I started to see how is the behavior of the robotic arm regarding the both controller. In terms of precision, PID was the best, actually. But in terms of controlling the energy consumption and the torques, MPC showed good results in this regard. But I was not satisfied yet. Why? Because PID and MPC both are linear controller. So, and as you know, the robotic arm is a nonlinear system. Everything here is nonlinear, by the way. So how you can control something nonlinear with a linear controller? The controller will have some boundaries, will have some limitations to handle the nonlinearities of the robotic arm. This is why I am trying now to use the nonlinear MPC and go forward to use the adaptive control theory, which is also a nonlinear solution, to see the results. Thank you for your attention. And if you have any question, please let me know. I am here.
Next speaker, Majid Khadiv is an assistant professor in the School of Computation, Information Technology at the Technical University of Munich. He leads the chair of AI Planning and Dynamics Environment at TU Munich and is also a member of the Munich Institute of Robotics and Machine Intelligence. Prior to joining TUM, he was a research scientist at the Empirical Inference Department of the Max Planck Institute for Intelligent Systems with director Professor Bernhard Skolkoff. Before that, he was a postdoctoral researcher in the Machines in Motion, a joint laboratory between New York University and Max Planck with Professor Ludwig Rigetti. Since the start of his PhD in 2012, he has been performing research in motion planning, control and learning for legged robots, ranging from quadrupeds, lower limb exoskeleton, up to humanoid robots. He has published 23 peer-reviewed journal articles and more than 21 peer-reviewed conference papers in these domains. He's currently an associate editor of the International Journal of Robotics and Research and has served for several years as associate editor in major robotics conferences such as ICRA, iRights, and Humanoids. Put your hands together for Majid Khadiv.
Thank you. Everyone, so thanks a lot for attending. I'm going to talk about some of my recent works on optimal control and learning for locomotion. So I'll start with a bit of motivation. So as Rabab just said, industrial robots have been there for more than 40 years or so. They are doing very precise stuff. They are assembling our cars. They are doing, very precise welding and so on. But the thing is that, these robots are not moving around and they're working in a very controlled environment. So I think this is a problem. Nowadays, we can see more and more of the robots going outside of this, controlled environment. They can move around and they can do, basic stuff like inspection and so on. But still, we cannot see that these things, these robots can do interaction with the environment or doing things that, we wanted to do, which are these kind of things, right? So if you look at on the left, you see an airplane factory and nothing there is automated actually. Or you can see here in our kitchen, none of our robots can basically clean this kitchen or they cannot do tasks like this and they cannot interact with humans. So this is what we want. So what is missing? I think we need to have robots that could go, everywhere that the human can go. We need to have a versatility like this, such that the robots can do tasks in such a difficult, situation. They should be dexterous enough such that they can manipulate this wide range of, objects you can see in this picture. And finally, and maybe less importantly, I don't know, maybe far into the future, they should be acceptable by human if they're going to be deployed in human settings. I believe, it's a personal view that humanoid is the best platform for this. Maybe it's not the most performant one for each of these tasks, but it's the one that can be used in all of these tasks. So I believe if we solve the humanoid robotics, we pretty much solved all the problems that we see there. If you disagree, you can just, comment or raise your hand. It's absolutely fine. And also just interrupt me if something doesn't make any sense. So this is super difficult. That's why we try to basically, deal with simpler problems like quadrupeds, bipeds, or fingers like, for manipulating objects. So the way I look at the problem is through the lens of optimal control, which was formalized by Richard Bellman. And basically in a very simple setting, so we want to bring a system from a state x0 to a final state xn. At each state xk, there is a random transition to go to xk plus 1, and there is a random cost associated with this transition, okay? And then the idea is that to minimize the cost and bring the system to xn. So this is the optimal control setting. So the main principle that I use for my research is principle of optimality that was, proposed by Richard Bellman. And basically in a very plain text, it says that, independently of the initial state and initial decisions, at each state, the remaining part of the decision should constitute, should constitute an optimal policy such that the policy is optimal, okay? So it's a very simple idea. And then basically, as Richard Bellman pointed out, this applying naively this principle to control of systems suffers from curse of dimensionality. What it means is that basically consider you want to move one point in the space, okay? You have 3 positions, 3 velocities. Now, if you only consider for each of these values 10 possibilities, you end up having 10 to the 6 possibilities. Enumerating over all of this is really, if you increase 6 to 7, so this was only 1 point, right? Now increase 6 to 7, you will be having 10 to the power of 7 possibilities. So this explodes exponentially. So I talked about only 1 point. Now how about this humanoid robot with something like 100, number of states is 100, and each of the states actually is continuous variable. So this explodes, and basically you cannot solve it, forget about it. But As I said, this is called curse of dimensionality, which was first, the term was coined by Richard Bellman. But as pointed out by Dimitri Bertsekos, there are many circumstances that actually we do not, basically we know the structure of the problem in advance. For instance, in robotics, we know physics of the system. We know the constraints of the system. So if we leverage that, then maybe we can, beat the curse of dimensionality and solve the problem. And the other thing is that maybe we do not care about the global optimality of our decisions. The only thing that we care is that we want to have something that works, which means suboptimal control schemes that make a balance between convenient implementation and adequate performance. And this is exactly what I do in my research. I try to find tractable approaches such that I can solve control decision problems for these kind of settings. So these are the robots I've been working on during the past 10 years, and I'm gonna show you some of the results. So I'm gonna talk about a bit of math, so bear with me if you have any questions. I try to simplify things such that everybody can understand, but if something is, vague, just ask, So to solve the optimal control problem for humanoid robots, there are 3 decision variables we are interested to find trajectories for. One is the interaction forces, lambda. One is tau, the joint torques, and one is q, the trajectory of the joint, right? Normally, we have a system with n, the degree of freedom of 50. So it's a very high dimensional system. And we have something like, m, the number of contact with the environment varies depending on the configuration of the robot with respect to the surfaces or the environment. We would like to minimize the cost functional like this, which is an integral of, sum of some cost into the future. And this is like, for instance, I want to track a trajectory, I want to minimize the energy, I want to minimize the sum of torque or something like this. And the idea is that I want to find a trajectory for those 3 variables that I talked about. And normally we have a terminal cost that helps us to provide some guarantees, right? We would like to bring the system to a terminal set such that we are sure that we are getting the behavior we want. So the main constraints of the system is physics, right? So we have rigid body dynamics, the simplest way we can write down the dynamics of the system. But there are a couple of problems there because actually these dynamics are highly non-convex. There are many sinus, cosine, sine and cosine are multiplied to each other. And if you just look at this dynamics, it's super nonlinear and non-convex. So it's difficult to solve this optimization problem because of this non-convexity. The other problem is that these robots are under-actuated. What it means is that basically you do not have tau or torque on each row of this set of equations. Some of them are 0, which means that the base of the robot is not actuated directly by any actuator, right? It's free. It's only actuated indirectly through these contact forces. And interestingly, these contact forces, the number of contact points changes over time, which means that the system is hybrid. And that means that basically the structure of the dynamics of the system changes depending on how many contacts you have. So this is even more difficult. For instance, if you have, I don't know, a quadrotor or I don't know, autonomous driving system, you do not have this change, right? And this is very simpler. That is very simpler than this. And this is the main problem in general in contact-rich problems. On top of that, we have constraints on the position of the joints, we have constraints on the torques, we have constraints on the forces, which are actually very nasty constraints because these are second-order cone constraints that are really difficult to handle in general. And this is really absolutely intractable to solve, okay, holistically. So we cannot solve this problem. It's super difficult to solve. I mean, you could try, but the problem is that it takes few minutes to solve based on the best solvers we have. And the other problem, the main problem is that actually it's not how fast we can solve it, it's about local minima. Basically, if we do not warm start, we do not give a good motion start as a starting point, this will get stuck to some local minima because the problem is highly non-convex, which means that most of these constraints will not be satisfied, which means that you will have some random motion, okay? So unless you have a very good warm start, this doesn't work well. So, and also again, we want to replan the whole trajectory for these systems. So we need to be able to solve this in the order of milliseconds, right? So to me, it seems impossible. So let's see what we can do for this. So the first thing we do normally is simplification. So here I show that basically the dynamics of the system can be split into 2 parts, right? There's no simplification yet. This is exact. So I can say there are 2 dynamics. The first part of dynamics is an actuated part, which is the relationship between interaction forces and motion of the robot. Okay, so this is the unactuated part because there is no torque, right? This is the 6 equations of rigid body system, right? Without any joint torque being involved. And the second set of equations are the actuated ones, right? So basically here I say how much torque I apply such that I have the relationship between the forces and the motion satisfied, okay? So until here, I mean, there's no magic, right? It's pretty simple. Now I make my first assumption. I say let's assume that I have infinite torque, okay? Just I relax the torque constraint. Now if I say that, then given a force and a motion of the system, I always can find tau from this equation. So I can get rid of most of the equations of this set of physics equation. So this is n equation, this is 6 equation. So now I only have 6 equations there. The other thing is that I got rid of many of the decision variables, which are the torques, and I only need to optimize over Q, which are the joint motion and contact forces. So this is already very much simplified. But interestingly, I can show that this dynamics can be exactly written down as this dynamics, right? So this is very simple dynamics, like interaction forces, the external forces on the system is equal to m times c double dot, which is the center of mass acceleration, plus g. This is Newton equation, right? So consider this whole robot as one rigid body. External forces is equal to acceleration, and here is the rate of angular momentum around center of mass. So now I have 6 equations, but not only that, I got rid of also Q, which is also n variables, and I replaced it by center of mass and angular momentum around center of mass. Now I also have only 6 variables for the trajectory of center of mass. Again, from here to here, there was no simplification. It's exact. It can be shown that this is exact. So this is cool. Now I only need to find the interaction forces and center of mass trajectory and angular momentum around center of mass trajectory, which are, each of them are something like 6 to 12 dimensions. So now it's under control. I can solve it. So this is called centroidal momentum dynamics. And now this optimization problem is basically based on only this assumption that I have enough torque in my joint. This is the only assumption. And again, I'm finding the K, which is the set of center of mass and angular momentum around center of mass trajectories, and the contact forces lambda, right? These are the equations of motion of the system. And this is basically the interaction forces constraint, which is the friction cone constraint, okay? So now I can solve this, and still this is non-convex. I'm going to talk about this later, but we developed the solver based on sequential convex approximation such that we can basically solve this optimization problem. And interestingly, we can show that if we solve this problem and we have center of mass trajectories, we can pass it to a only kinematic solver such that we track the center of mass trajectories, okay, and find the joint trajectories, considering the constraints that I have on the contact and so on. And if we go back and forth between these equations, okay, there's no guarantee, but sometimes it converges to a solution that satisfies the constraints of both problems. So this is called block coordinate descent approach, okay? You go back and forth between two optimization problems, and then, I mean, it's more detailed. I don't want to go through it. I'm just giving you some high-level idea. But if it converges, it means that you have a trajectory that is consistent both in terms of the force trajectories and full body trajectories, right? So this would be great, but normally, actually, it doesn't converge. So this is the problem. So what we do is that we say, okay, we only do one dynamic, path, one kinematic path, and that's enough. We pass it to the robot to see what happens, and normally it works. But I mean, it's not exact. I made simplification. Now, if someone gives me contact plan, which means, which end effector goes to contact next, I can generate full body trajectory by this, pass it to a simple inverse dynamics, whole body controller to generate torques from the trajectories, and then I can, implement this on the robot. And actually, it's very successful, this approach. I can generate some type of multi-contact motions, fully automatically. And here, for instance, the robot is able to jump something like 5 times its standing height using, this trajectory optimization approach. So here, this part is offline. So I generate trajectories offline, and I only rely on instantaneous controller inverse dynamics such that I can stabilize this or track these trajectories. So this is nice, but we wanted to replan trajectories. So we wanted to do the whole thing through model predictive control or MPC. But the problem is that, this is expensive to solve because we have a multiplication of center of mass to the interaction forces. And this is a non-convex term because, you have bilinear terms of center of mass times force. And this makes the problem super difficult to solve, and it takes time to converge. But recently we have developed a solver based on alternating direction method of multiplier. It's called ADMM to solve this. And actually this is super fast to solve. So the way we do it is very simple. The high level idea is this. So you keep the C fixed, solve the problem for lambda, okay? Find a solution, and then use the solution, put it here, keep it fixed, and now solve for C. And each of them are convex problems. By going back and forth and also updating the Lagrange multiplier, you could basically show that for convex problem, it converges to the minimum of the system, the global minimum. But this is a non-convex system, so it converges to a local minimum, but still it's fine. And it's a good trajectory. With this trick, now it's not anymore expensive to solve this problem, and we can do MPC on the real robot. So this is full body nonlinear MPC, right? All of these things are replanned using at every 50 milliseconds, so at 20 hertz. So this whole trajectory optimization problem together with inverse dynamics is solved at 20 hertz, and this gives quite a lot of robustness to the system that it can handle uneven terrain and so on. Okay, this is good, but here I consider that the contact is fixed, the plan is fixed. Now if you have an environment that is limited like this one, now actually I need to find which surface I select next, such that I go to contact and I have, I go to a desired point at the end. And here we combine this with the Monte Carlo tree search, which is a search method for discrete variables. And then we combine this with nonlinear MPC, but this MCTS takes time because it uses nonlinear MPC to evaluate the possibility or feasibility of the trajectory. So we just did a supervised learning on the map of the environment to give us the contact plan. And with the contact plan, I mean which end effector would go to next to basically to which surface. And this means contact plan. And actually, so now every decision is basically automatic. So the robot selects the optimal set of basically contact locations such that it goes from the one corner to the other corner. And sometimes actually it comes out with very interesting solutions. Here you see a lot of these are missing, the blocks. So it needs to do some weird motion to go to the end. And this is fully automatic, right? So the contact, selecting which surface to go to contact next is fully automatic, right? So back to nonlinear MPC. So we said that, okay, now we can do 20 hertz MPC. This is great, but still there are problems. So again, as I said, this is still non-convex. So basically what we do is that we did 50 iteration of optimization problem of convex one each, right? Which is quite heavy and it's not parallelizable. So you need to sequentially do this. And we use an external computer to solve this, right? So forget about doing this on board of the robot. So this is still expensive. And the other thing is that we did not optimize for the timing of the contact and location of the contact, which means that if you push the robot, it cannot adapt its behavior because these are fixed. If I start to optimize those as well, the problem is that the computation time becomes double or even more. So then again, you cannot do MPC. So this is the problem. That's why basically here we kept it fixed. Yes?
Can you clarify the term convex?
So convex is, So basically we have two notions of convex. When we talk about convex function, it means that basically, so let's start with the convex set. So if you have a set, if you consider 2 points inside the set, if you draw a line between these points, the whole line should be inside the set. This is a convex set, right? And convex function, like this function, if we consider the epigraph of this function, then it should be a convex set. This is the definition of the convex function. So in order for an optimization problem to be convex, okay, the cost function should be a convex function, and the inequality constraints should be convex sets. Equality constraint should be linear, because only a linear function is a convex set. Because if you consider a line, if you put two, there's only line can be convex. So this I mean by convex. And then for convex problem, we have super efficient solvers. And really, you can solve the full optimization problem in microseconds or something like this. But as soon as it becomes non-convex, it means that you need to do multiple iterations of convex optimization. It's called sequential convex optimization. And then that is order of magnitude more expensive than a convex problem. But the thing is that the problem is so complicated that we cannot make it convex unless we make so many assumptions on the problem. Any more question? Sorry, again, if I do not explain something, just ask, because I'm explaining things too abstractly, I would say. So if you are interested in some part, I can explain in more detail. Okay, so these were the problems. So first, it's very expensive to solve this. Second, we are not still optimizing some part of the decision variables. So in order to do that, we need to make more assumptions. There's no other possibility. I mean, I would say that was the most efficient way we could solve the problem, but still it's very difficult. So now if I make a bit more assumptions, like if I say the external forces pass through the center of mass, which means that the rate of angular momentum around center of mass is 0, and the center of mass moves on a certain, predefined manifold. It can be anything, right? The shape doesn't matter. It should be predefined, right? For instance, for walking, you can say center of mass moves on a plane. For running, you could say it moves on a, parabola or something. If you assume these two things, then we could show that the non-convex part of the dynamics can be written down as two linear dynamical systems. This is called center of mass dynamics. So if you know basic control theory, then we have C dot here, we have minus C here, which means that the system is stable, right? Which means that center of mass converges to this variable, which is called divergent component of motion, DCM. And then if you look at the DCM dynamics, we see psi dot here and plus psi here. This is a basically unstable dynamics, right? So this diverges from P, which is the contact location or center of pressure. So it means that if I walk, the divergent component of motion just diverges. And if I do not step in that direction, the system will fall down, right? It simply means that. And with using this kind of, separation, now actually we show that we can write down the dynamics of the system as a linear function of exponential of the time of the gate and the contact location, basically. And this is great because now we have a convex optimization problem. Based on those, given those assumptions, right? This limits the range of motions we can do with this optimization, but at least we have basically now convex optimization. So we have convex optimization, easy. We can do now 1 kilohertz MPC on this system. And now, again, if someone gives me contact plan, for instance, for walking, it's simple, right? Because it's right, left, right, left. So the contact plan is very simple. I can adapt the step location and timing using this convex optimization problem, and then I can pass it to an inverse dynamic solver to find the full body torques of the system. And then with this, we were able to actually have very robust set of motions on our real robot. So what the robot does is that it gets the feedback of the base, and then what it does is that it's adapting all the time its location and time of contact, such that it recovers from some disturbances. So here I'm moving around basically this platform, and the robot is adapting contact location and timing to recover from these disturbances. So we can guarantee some things, like something is called viability kernel, which is related to maximum invariant set in control theory. And viability kernel means that, it's the set from which there exists at least one control sequence such that the system doesn't go to the fail state. For locomotion, it means that the system doesn't fall down, okay? So this viable set, finding it is intractable for locomotion in general, but with the simplification we did, we could actually compute the exact viability set and put it here as a terminal constraint to the problem, which means that now we have guarantee of viability, which is, you could say it's a stability constraint, for instance, for constraint system, because in the Lyapunov theory, you do not consider constraint system, you only consider continuous system. Here, if we consider constraint system, then viability is basically somehow related to stability. Not exactly, but it's related to that. And with this, optimization problem, actually, we could guarantee viability, which is, a big deal, but we could only do it for the simple system. For general nonlinear system, there is no guarantee. We do not guarantee anything. So we just tune things such that they work properly. But this one has guarantee. And to show that it's a general approach, actually, we tried it on these 3 robots and worked very well. So you could see for the quadruped. And actually, we could show that this works also for running. So the only thing you would need is that you need to change the manifold of the trajectory of center of mass in Z. And that's it, right? You are adapting a sublocation timing at 1 kilohertz, so you could do push recovery, switching between walking and running, also walking on uneven terrain. Okay, that's good. But if you have worked with robots, you know that all the things I show in simulation, when I start doing on the real robot, this is what happens. There are many failures. I'm sitting there with this, stop. I'm very careful that I don't damage a robot, but we break a lot of robots. It's a very demanding task sitting there and tuning parameters of these controllers, And it would be nice if we could do this automatically. And this is another project we did with another student of mine. And basically, we started using Bayesian optimization to optimize the cost of the MPC. So what we do here is that we get feedback from the behavior of the system. For instance, if the robot wants to track a velocity, the performance is to maximize this. And if the robot falls down, we give a high penalty to this optimization problem. Basically, this is a black box optimization problem, but it's very sample efficient. I mean, I don't want to go through the detail, but basically, it's something that people use a lot when you have a certain number of parameters of controller you want to automatically tune with a few number of experiments or simulation. So now if we look at the cost function we have in our MPC, we have normally a term which is related to performance. For instance, velocity tracking for a robot going in different directions. We have certain constraints, right? For instance, when the robot is walking, the foot cannot go beyond some reachability set, right? So we have these constraints. And basically, if we do not regularize this solution, if we put beta and delta, for instance, to 0, what happens is that the optimizer finds the solution on the edge of this constraint, which is the most risky solution. Why? Because it's optimal, optimal for tracking having the best performance. So it's important that we basically increase beta and delta such that we push the solution away from boundaries of constraints, okay? But this comes at the cost of, degrading the performance. And sometimes at the cost of, losing the viability or stability of your program.